The lesson objectives were to review some theoretical concepts about vectors in two dimensions and to represent them on the Cartesian plane. To activate my students' problem knowledge, I asked them, do you think that numbers are applicable for real-life context? They gave me some examples, and on what we agreed was that when we go shopping, numbers are helpful, especially to estimate how much money we are going to spend to buy something that we need or like. For example, if your mom gave you $10, probably your mother told you to buy some eggs, and it is about $1.25. And you like force. Do you know what is a force, guys? A force, something like this. That women use to ring, yeah. Okay, or a band, yeah, force or band that you like very much. And it is about, let me see, about 50 cents. And your mom gave you $10. Can you buy the force of the band? Can you buy? Yes or no? Yes. No? No? Okay, let's count. Yes, count. 25 cents plus $1 and 25 cents, how much is it? $1 you get 50 cents. Okay. And you like this is a bag so nice that you like, and you see the cost, and this is $8 with 50 cents. So can you buy that bag? Yes or no? Yes. Okay. You can buy. What about if the bag costs 19? No. No, I can't. Can you buy? No. No. You can't. Okay, very good. Let's continue. So now today's topic is vectors, right? So do you think that vectors are applicable for real life context? Yes. Yes? Can you give me some examples?
For example, when you are in a place and you want to get in another place and you say to somebody to give the directions and the person for example it's train something like that.
Vectors are vital or very important for real life, especially for people who work with subjects such as physics. Yes or no? Physics, okay, applied mathematics, and engineering. Okay? So they use vectors to calculate, to estimate weight, to estimate speed, to estimate acceleration, okay? Many forces to construct some machines. For example, the tractors, the cars. They think about that to build those equipment for human beings. Okay? What is the meaning of machines? Doesn't matter. Yeah. Let's see. Machines. Yeah. Okay. To build up or to construct some machines, they estimate or they use vectors.
speed is what you say velocidad. Okay? So speed. In what units? What units do you need to measure speed? In seconds. Kilometers per hour. And meters per second in your case. Okay? The units that you use to represent. Yeah, per hour. Kilometers per hour. Very good. Okay. And also you can, the money to represent how heavy is something. Yeah, how to do, for example, this table, how heavy is it? How heavy is it? You can use, what you can use? And the other component, okay? Let's talk about the other component, which is direction. In the real life, we use the compass, north, south, east, and west. Very good. This is northeast, east, southwest. Here, southwest. Here, northwest. Okay. Now, a vector is represented with a letter of the alphabet. Okay? With a letter of the alphabet. For example, we have the vector A, vector B, vector C. Okay. Also, vectors are graphically represented in the Cartesian plane. Okay? A vector has two components. Okay? Two components. An horizontal component and the vertical component.
Next, my students watch a video which help them to listen authentic information about what are vectors and how are they represented on the Cartesian plane.
Welcome to the Science Asylum. I am Nick Lucid. A lot of people say they don't like numbers, but they're kind of unavoidable. I mean, we run into them all the time, keeping track of account balances and speed limits and travel times and tip percentages. The list goes on and on. When you think about it, numbers really aren't all that bad. When they're just numbers anyway. Dun, dun, dun. In science, the familiar numbers are called scalars to distinguish them from other types of quantities. Most other types are only used by scientists and engineers, but the vector is much more common. Vectors are used very often by programmers and pilots and police, even park rangers, whether they know it or not. Formally, we say a vector is a quantity with magnitude and direction. What the heck does that mean? Yeah, I know, it sounds horribly complicated. Let's break it down. Okay, so being extra careful here. A quantity is something you measure with a number. A magnitude is a size. So in this case, it's just the size of the number that was measured. The direction is what distinguishes a vector from other quantities. There are a ton of things we measure that have direction. Position is weird though because the zero is kind of up to you. If you can understand how position works as a vector, then you can understand how all vectors work. So we're going to use it as the example for the rest of this video. In order to work with vectors, we need a coordinate system. The term coordinate system sounds kind of fancy, but it's just a collection of numbers assigned to places. We do this all the time with room numbers, building floors, addresses. Unfortunately, those systems aren't patterned enough to do the math that we need to do. If we're labeling position on the Earth, the most widely used system is longitude and latitude. The zero is located here, and you count from there either north, south, east, or west. The location given in the police call is a little over 42 degrees north and a little over 83 degrees west. So cool! Yeah, I know, right? I'm going to be a huge bore though, and use the standard Cartesian coordinate system. It labels one direction, the horizontal, with X values, and the other direction, the vertical, with Y values. And along each of those directions, you can be either positive or negative. Bam! Solution! It's extremely mathematical, I know, but that's what makes it so handy.
Once students watch the video and negotiate meaning, for instance, asking some phrases or words that they needed extra information to clarify their doubts, I ask them some questions, such as, are vectors applicable in real-life contexts as numbers are? What professionals use vectors on their daily labor? What properties does a vector have? How are vectors represented? Then, I ask my students to watch another video about the same topic. But now they will integrate the information provided by both sources, video 1 and video 2.
Let's start by asking the most basic question, what is a vector? And a vector is really just two pieces of information, direction and length, or what's also called magnitude. Two different words for the same thing. Now, length is a very physical, visual concept, right? It's something we can see, it's something we can measure. And the same with direction. It's our orientation. It's a very visual thing. So vectors, to begin with, most intuitively fit on a graph. They fit in a place where we can visualize them. And so how could we attempt to capture direction and length? Well, you know, I think an arrow does a pretty good job. This, for instance, captures direction. It's moving in the northeast direction, and it also clearly has a certain length. And so this is a vector, and that's exactly how we graph vectors, just as arrows. This is also a vector. It's pointing in a certain direction. It has a certain length, as is this. So is this. This is a vector. Even though it doesn't start at the origin, it's clearly pointing in a certain direction, so it has direction, and it clearly also has length. So vectors need not start at the origin. They can start anywhere. This is also a vector. It's pointing in a certain direction, and it has a certain length. Okay? That's great. Now let's look at a specific example. Here is a vector, and I want to, first of all, name that vector. So I'm just going to call it V, and I'm going to put a little arrow over the top of it to make sure that we know that this is a vector. So the vector V, and now I want to capture this information. I want to capture the information that arrow is telling us without needing to draw it. So I can't, I'm not going to write this like this. I'm not going to say V is equal to this arrow. That's too ambiguous. I need something more definite, something with more structure. Well, this vector moves over a certain amount in the x direction. Let's say, for example, it moves over 3 in the x direction. It also moves a certain amount up in the y direction. Let's say, for example, it moves up 1. Well, now I can say that this vector is equal to its components. So that's a new word for us. It's equal to its x component, which is 3, how much it moves over in x, and its y component, which is 1, which is how much it moves up in y. So again, this is the x component and the y component. And now anyone in the world looking at this vector, v equal to 3, 1, can go ahead and draw that vector if they want to. They know exactly which vector we're talking about when we write that.
Similar as in video 1, I ask my students to answer some comprehension questions. Next, I asked them to practice what they have already learned.
Now, what we are going to do, guys? I am going to give you a paper, and you are going to draw some vectors. Okay? You are going to draw the vectors on this Cartesian plane. Alright, please, guys, write your name there. Write your name there. What we are going to do, guys? We are going to draw the vectors that you have there on the Cartesian plane. Please, let's do that. First, we are going to do it individually, and after that, we're going to compare and we're going to check your answers. No. You have to, okay, guys. Good question. Let me see where it is. You have to represent each vector of one Cartesian plane. Okay, you have 6 Cartesian planes. Remember that a vector is represented with an arrow. Okay, so it's required to draw an arrow.
Let me see. Okay, what is missing here? Remember that a vector is represented by an arrow. Look, what is an arrow? Okay? So here is missing the tip of the arrow. The tip, what is the tip? Tip of the arrow is missing this part. The tip. You have the arrow, but it means the tip. Draw the tip. The tip. Yeah. Okay? It's missing. Very good. Very good. Okay, let's see. Teacher, ¿verdad? Okay. Es así, 1, 2, 3, 4, 5. 1. Okay. There's A. Okay, you are drawing vector A, right? A. You have on the horizontal you have 3. Very good. And on vertical you have 5. 1, 2, 3, 4, 5. Very good. You have the arrow there. You have named the arrow as well. Very good. A, B, C. And here it's missing the tip of the arrow. Do you know what is the tip? The tip of the arrow. Okay, this is an arrow. Yes or no? Yes, yes. If you don't draw that, it's no vector. Okay? Okay? Yes. Yes. Okay, very good.
Okay, guys. Now what we are going to do, have you wrote your names there? On the paper? Yes. Have you? Yes or no? Yeah. I need to collect your work, okay? And we are going to exchange our sheets in order that the others can check our work, okay? So let's write the names, okay? Very good. Okay. Now I am going to give you the work of the partners. You are going to check if they are right or not. Okay. Guys, we are going to check on the board. Okay, we are going to check, and you are going to help me as well checking your partner's work. Okay? Okay. So now let's start. Let's draw the first vector, vector A. Is there any volunteer who wants to come to the board? Silence, please. the name of the vector. Okay, what is the name of the vector? 3. Yeah. The name of the vector its component, the horizontal component is 3 and the vertical component is 5. Okay, very good. Now, I need another volunteer to draw the second one. Okay? Salome, the second one. Let's pay attention if she does it correctly. Okay? Let's pay attention. Salome, you have to locate the horizontal component. Yes. Okay. Which is? Okay, very good. Do you think it is right or it's wrong? Right. Do you agree with Salome's answer? Yes or no? Yes. Okay. So its horizontal component is -2 and the vertical component is 5. Okay? Very good. Now let's continue. Another volunteer for the next vector. Nayeli? Come to the board. Let's see the other one. Do you have a ruler? Let's see. Is it right? What is missing, Nayeli? What is missing? Escríbelo. What is missing? The name. What about it? Thank you, Nayeli. So we have the vector C with its components 4 minus 3 minus 3. Something like this, okay? Okay, very good. Now, another volunteer is Katia. Okay? Please, guys. Please check the work of your partner and draw a tick if it is right. Yes, sir. Okay. 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 It doesn't matter. We are just practicing. Okay, don't worry about race. 1, 2, 3, 4, 5, 6. Okay, now let's check. Katia, can you tell me which is the horizontal component? Minus. Okay, and which is the vertical component? -3. Very good.